Hello everybody and welcome to our CNC Milling demo on the HAAS VF-2SS. What we're going to do here is show a demo part being machined so that you can hopefully see how this machine works and make some connections between what happens in NX CAM software and what happens in the actual machine. So what we're looking at right now is the inside of the machine. The table is down on the bottom center. The cylinder in the upper right is the spindle. So my tool holders will get inserted in there and that spindle will drive the rotation of the tool. The black arm you see to the left of that is the tool changer arm. So it has a little gripper on each end that kind of flip-flops out the old tool that's in the spindle with a new tool from the holder. So here we go. There's nothing in there, but it put a new 1/4 inch end mill in there. And we're doing this actually at 25%. And now 1/2 inch end mill at 50%. And finally, we're going to put another tool in there, quarter ball at 100% speed. So you can see the rapidness with which that tool change occurs. All right, next thing we're going to do are what are called rapid movements. We're going to start at 5% on the way down, then move to 25%, then 50%, and finally 100%. What a rapid movement is a non-cutting move to get you from point A to point B as quickly as you can. A G01 is a cutting move with a specified feed rate. We're going to start out here just going around the perimeter, not cutting anything, just demonstrating what a cut speed of about 24 inches per minute looks like. This is a cut speed we would have typically with a 1/16 inch diameter end mill, right? A small tool. And now Eli's going to actually speed this up here manually on the machine so we don't have to sit and watch it putter around there, right? Just to give you an idea of what the cut speed looks like. We're going to change it out now to a 1/4 end mill, I believe. And we're going to do the same thing, cutting air around the perimeter at 48 inches per minute. Now our 1/4 ball mill typically cuts at this speed. This 1/4 end mill is actually a 3-flute tool instead of a 2-flute tool, which means it can cut 50% faster, right? So it would actually cut at 72 inches per minute. Remember, cut speed, or at least we'll learn, cut speed is dependent upon the number of flutes on your tool, the chip load, and the rotational speed of your tool. All right, so 3 flutes can cut 50% faster than a 2-flute tool. Now we have a 1/4 ball mill. We're going to go at 96 inches per minute. Again, just to give you a sense of how fast these things are moving. We wouldn't cut that with this ball mill, but we would with our 3/4 inch insert tool, the Beast. And with a 1/2 inch end mill, we'd actually cut a little faster at 108 inches per minute. Next thing we're going to do is show you the way in which a tool can engage with the workpiece to begin cutting. So the first one's just going to be a plunge. It's basically a straight down dive to drill an initial hole into the workpiece. And then we do a little quick profile to mill away part of the pocket. And then we lift out. That's called the retract. And then what we're going to do, I think we're going to zip up. So, oh no, we're going to use the same tool. All right, next entry type is a ramp or a zigzag. This is a straight line angled motion. We're moving in the X and the -Z direction simultaneously. It's a little safer way to kind of angle our way into our material rather than just kind of diving straight down in. And we would use something like that if we don't have what's called a center cutting tool. Finally, we'll use kind of a ramp that follows a spiral, right? Kind of a circular downward path rather than a linear downward path. And it's just another way of getting into our workpiece, maybe when we have a little less space to fit the tool in there. And again, so notice on all 3 of those, the speed at which we engage the part was actually lower than the cut speed. That's because when we engage the part, we want to be a little more gentle with our cutting. All right, so we'll talk about that later. Now what we're going to do is we're going to actually cut part of the pocket using a cavity mill operation with a spiral cut pattern going from the middle of the pocket out. And we use a 25% depth of cut. Here we're going to flip to the other side and we're going to use a zigzag pattern. Same 1/10 of an inch depth of cut, 10% step over, sorry, and 60 inch per minute feed rate. Next, what we're going to do is we're going to move back to the front and we're going to repeat that spiral out cavity mill operation, but we're going to do it with a 25% step over. So we're just cutting with a wider path as we move around. So this is more aggressive, gets the job done faster, but it also puts higher loads on the tool, generates more heat, can tend to deflect the tool, wear it out more quickly, and possibly break the tool when you cut more aggressively. Here's the same thing, 25% step over, zigzag cut. And now we're just going to finish up milling this cavity. We're going to do the full pocket, spiral cut out, 1/10 of an inch depth of cut, 25% step over, and actually a very high feed rate, 180 inches per minute, which is much more aggressive than we could be with aluminum in these cutting conditions. Again, we're cutting wax, right? So it's very friendly material to cut, has very low strength. All right, so notice in between each depth that we cut in these pockets, the tool moves up and out and then back in. Right, that's called a retract to lift up and an engage. Again, we're using a plunge here. That's a setting that you can change, but typically we kind of get up and out of the way so we can move back to the start point without running into anything in your part geometry. Now we're going to continue to remove material on the outside of the raised pocket using a cavity mill operation. A little bit more aggressive. I think it said we were using a 25% step over, maybe 40%. But we're going pretty fast, I think 180 or 240 inches per minute it said. So we're just removing material from the outside, traveling around in the XY plane at a given Z depth. And what that does is it gives us this little stair step appearance on the outer angled surface of that raised pocket. We'll come back later with what we call a contour operation to kind of take off those ridges or stairs and get kind of that smooth, flat, angled surface that we want in our final part geometry. So what we're doing here is we're kind of roughing. We're removing material as quickly and as aggressively as we can with a big tool, and then we'll come back later with a smaller tool and clean up the details. So we're going to come over to the other side here, do the same thing, but with 3 times the depth of cut, right, 3/10 of an inch. Notice we're being so aggressive that we're actually breaking material off. We're fracturing that wax rather than cutting it in a controlled fashion, and that is definitely bad. If this were not wax, we probably would have broken our tool by now, but if you're breaking material off in an uncontrolled fashion, you're going to have problems getting the geometry you want. All right, that higher depth step also gives us a much rougher stair step appearance. So we have about 3 steps instead of about 8 or 9 steps. Now what we're going to do is a contour operation. We're going to come back with, in this case, a 1/4 inch end mill. We're going to use a spiral cut with, I think, a 25% step over. And we're going to ride that tool right along the surface. So we're not really doing depth steps. The tool is constantly in contact with the surface, and it's moving kind of full 3D. It's moving in the X, the Y, and the Z directions. Not necessarily all at the same time, but it can be. So we're doing 25% step over, 150 inches per minute, and really we're just kind of skimming off those little raised ridges, those stair steps, and revealing a surface, an angled surface that's closer to the geometry that we want. Now we still have a stair step appearance on here, but it's much, much finer, almost to the point that you actually can't notice it unless you look very closely. Now in the front half here, we're going to do a similar operation, but with a 1/4 inch ball mill using a 25% step over, and we're going to cut with a zigzag angle. And you'll see that we get a different looking surface texture on here. One thing I want to point out while this is going on is that we have used what are called trim boundaries to kind of split up the machining between the front half and the back half of this part. What a trim boundary does is it allows you to select the surfaces you want to machine, right, pretty liberally, and then use a trim boundary to kind of define exactly what regions of those selected surfaces do or do not get machined. So it gives you a little bit better control as to where the tool does or does not go. Okay, so we're almost done here. You can see on the front end of that, I have this very rough kind of set of raised ridges that are called cusps. I'm going to come back with that exact same tool. I'm going to do a zigzag cut pattern, but in this case I'm going to use a 10% cup step over. Those raised ridges are basically ridges in between the little circular, semicircular grooves that are created by that contouring operation. So if I reduce the spacing between 2 subsequent zigzag passes, I reduce the height of that ridge. And if I make that step over infinitely small, the ridge height goes to 0 and I get the perfectly smooth finish. But then it also takes me an infinite amount of time to machine. So we've reduced the step over to about 10% here, and that gives us a pretty good surface finish for most of the things that we want to do. For example, injection mold, make an injection mold tool, right? So much better surface. So typically, any surface that's visible on your car that you want to have a good finish, you'll do a 10% step over contour to get a good surface finish. Last thing we're going to do is go back inside that pocket and clean up our inside corners. They actually have an 1/8-inch fillet radius. Right now, as cut, we have a 1/4-inch fillet radius because we cut that with a 1/2-inch diameter end mill. So we're going back in and we're doing what's called a profile mill, kind of one lap around the perimeter. And the only time we're really cutting is right when we get in those sharp corners where the excess material is. The rest of the material on the straight walls is already gone, so we're wasting our time cutting there. So a different strategy we can use is to use what's called a reference tool or in-process workpiece that allows the CAM software to figure out where exactly there's material to remove and only focus on those regions and kind of skip over other places where it doesn't need it. So you'll see here, it's kind of going to the corner, removing that material only in the corner, and then it's bouncing to the next corner. So this can be a little bit more efficient method for material removal. And we'll cover this in more detail during lab when we talk about the capabilities of NX CAM. So I'm hoping that this gave you a little sense of what happens on the actual machine so that you can connect that to what you're doing in NX.